straight away by starting the recording. And so for the today's lecture, we are going to, this is chapter 9. So just to let you know, so everything up to chapter 9 is now available in your Google Classroom. So any of you need to download, you can do it. And just remember that all these material that is available are PowerPoint presentation. Some of them are shared as Google Slides to make sure that it's easy to access for everyone. So make sure that you don't do yourself any alterations for those, because then it will be harder. Because you can do edits in that, right? So when you have the Google Slides, but at the same time, if you need to make any notes or anything like that, you can do that as well. So that's why I keep it in that way, right? But if anybody needs like PDFs or something like that, I mean, you can just save it as a PDF and convert it to a PDF if you need. And all the recorded lectures are also available in as YouTube links for you. So all of you should be able to access all the lectures that we have done up to now, right? Right. So basically, the first part or the first 8 chapters that we talked in this course is about up to our solar system and different instruments, coordinate systems, those kind of introductory section. And today we are moving to the next phase of this lecture series, that is to talk about stars, right? Now we have already discussed about one of those stars yesterday, so that is about our sun, right? Sun is just one of those stars. And in this particular lesson, we are going to look at the properties of the stars, right? So when we try to study about the stars, there is a kind of the first thing that we have to do is to look at how to study these properties of stars, right? So when you take a star normally has different properties. Now in this chapter, I am going to introduce these properties to you, and also we will discuss how we can measure those, right? And after that, the plan is actually to look at step by step what happens to these stars during their lifetime, right? So that is the most probably most of the content in this phase of lectures will be about discussing the life of a star, right? So how they initially start their life, and what do they during their life, and then depending on different properties, what will happen to them at the end, right? So that's what we are going to discuss during this phase of lectures. And to start with, now when I tell about that we are going to talk about stars, this will be the picture that all of you may have in your mind, right? And this is a picture of the night sky when you have a very clear night without any lights, right? So this is a picture taken from Canary Islands, one of the great places to observe the sky because of its clear skies and also dark, clear and dark sky. You should be able to see a nice constellation pattern here. You can see there are bright stars, 1, 2, 3, 4, 5, 6 stars right here, and this pattern normally extend to the other areas as well. So this is a constellation called Ursa Major, right? Or the Big Dipper, right? So this is something that you already know, that we have talked about the constellations in previous chapters, right? Now, so what we are going to discuss in this particular chapter is actually how these type of stars are born, right? And what are they made of, and how far away they are, and how long they will live, and how they will die, right? So these are probably the questions that we have in our mind about stars. And I have these questions with me, and I have some answers that I would like to discuss with you, right? And I hope all of you also will have same kind of questions, because when you look at this particular image right here, you can see large number of stars, and some of these brightest stars you can see clearly as a pattern, which we called as constellation. But this is all what we can observe from my naked eye, right? But we do not have any idea about what are the distances to these stars, and what kind of material that they have inside these stars, right? And also what will happen to them during their lifetime, how long they will live, right? Because what we can see during our lifetime is, if you, for example, if you look at this constellation pattern, this will be like this forever, right? So that's what we feel, because even when you say, when you become like 50 years, even after 50 years, we will have uh, again, we will have like different, we do not have any changes, right? So what we will have is the same kind of set of stars. So our feeling seems to us like that these stars may not change, right? So it looks like it's the same stars even after 50 years, right? So in general, we normally used to think that these stars won't change; they will be like this forever, right? But that is not the case. So we will learn in this chapter that how these stars are born, what they are made of, and how far away they are, and how long they will live, and how they will die. So these are the questions that we are going to answer, and not even within this lecture, during this series of lectures about stars, these are the questions that we are going to ask, right? So I hope this will make it clear for you what kind of things that we are going to discuss, right? So so by the end of this phase of the lectures, this is exactly what you need to know from this particular lesson, this set of lessons as well. So you should have an idea about how these type of stars are born, what they are made of, and how far they are away, and how long they live, how they will die, those kind of things, right? Right. Now, if you look at different properties of the stars. Now, to start this discussion about stars, I am first thing I will going to do is I am going to discuss about different properties that the stars could have, and based on the variation of these properties, we can get answers to those questions, right? So that is the idea. Now, in today's lesson, we are going to look at these different properties of the stars, right? So the number one, of course, the brightness of a star, and it's obvious, right? So even in that image that I showed you, some of these stars are brighter for you, some of them are not, right? So there are certain stars that we know that we even cannot see from our naked eye, because they are not bright for us, right? And in the color of a star. So that is again something you can get an idea if you go outside and look at the sky very carefully. We used to tell that all the stars are blue, but that is not the case. If you go outside and look at the stars, there may be some stars that has a different color, right? So some are like has a yellowish color, and some of these stars have a color that is, looks like a little bit towards the red color, those kind of colors, right? And apart from that, in astronomy, there is a different way of, defining a color, right? So I will show that to you during this lecture, how to define the color of a star. And the other thing is the distance, right? Distance means how far away a particular star is, right? Distance to the star. And then the size of a star, right? This distance means, that we do not have any idea about these stars that you see, like how far away they are. So there are different techniques that we use to measure the distances to stars. right? So we cannot use your day-to-day techniques that we are using to measure distances on Earth, right? Because these stars you cannot touch, you cannot reach those. So there should be a different mechanism to measure the distances, right? And then the size of the stars, right? How large they are in terms of the surface area, volume, or those kind of things. So that is one property that we are going to look at. And then the temperature of the star, right? Temperature is another important factor. And then the age. So how old are they? Whether they all like 10 years, 20 years, whether these stars kind of, old like billions of years. So that's something that we have to look at. And at the end, we should, by combining all these properties, we can define another property that is called life expectancy. So that means how long they would live. Now, you all know that we have a life expectancy, right? Normally, we expect that maybe a person may live like maybe close to 70 years, right? Or maybe a little bit more than that, like that. So that is called life expectancy of a person, right? Now, so let's look at these properties one by one. And first, I am going to start with the luminosity, because the luminosity is something that is connected with the brightness always, right? The luminosity is defined as the total amount of energy at all wavelengths that it emits per second. Now, within 1 second, the amount of energy that is emitted is normally defined as the luminosity, right? So that's the definition, right? Now, in astronomy, when we need to compare the luminosity of two stars, we use a different unit, right? To make the comparison among stars easy, astronomers express the luminosity of other stars in terms of the sun's luminosity. So we have a different unit for this. And so we normally express the luminosity of a star in terms of the luminosity of the sun, right? So as an example, if you take the star Sirius, we used to tell that it is about 25 times that of the sun, right? So it's 25 times luminous compared to the sun, right? We use this symbol right here, L, and this is actually not zero, by the way, right? So this is a different symbol to express the sun. So when you have this symbol, in any way, you should understand that this means sun's luminosity, right? Now, in our example, if we want to write the luminosity of, luminosity of the sun, this is how we are going to write it, 25, and this L, this symbol right here, right? So this is called 25 times the luminosity of the sun. And this will give you an idea about our stars as well, even though it seems for us that sun is very luminous. I mean, we expect that the sun should be the most luminous, most brightest star, right? But if you look at in terms of the luminosity, you can clearly see that the star Sirius is more luminous compared to the sun. In fact, Sirius is 25 times bright luminous compared to the sun. And can anybody tell me then why sun looks brighter in the sky compared to Sirius? I mean, it is very clear right here that the sun is, Sirius is 25 times luminous compared to the sun, right? Then why we see as the sun is the brightest star? Sun looks brighter for us, right? Not Sirius. It's very clear now. Can anybody tell me a reason for that? Why is that? So just think about for a minute. So I'm just going to stop the lecture for you to allow some time to think about that, right? Why sun is brighter? I mean, it's very clear from this data that Sirius is 25 times luminous compared to the sun. But when you look at the sky, this is not what you see, right? So what you see is the brightness, and it is very clear that the sun is brighter. There is a huge difference between the brightness of Sirius and the sun. Sun is very bright for us, right? And anybody have any idea why that happens? What is the reason? Right. Thank you for the answers. So that's the exact reason. The sun is very close to us, right? But the Sirius is so far away. So this makes the difference, right? Now it is very important that this is very simple thing, but it is very important that you understand this when you go through these lessons. So that's why I asked you the question, right? Now we have to be, this implies for you that we have to be very careful when you define something in astronomy, because it seems sun is brighter for us, but in terms of the luminosity, sun is not the bright. I mean, sun is not luminous as Sirius. And Sirius is the most Sirius is more luminous, has a higher luminosity compared to the sun, right? So that is basically based on the distance. Because the sun is closer to us, we feel it as a brighter object. But in terms of the luminosity, uh, sun is actually not the most luminous one, right? Because we feel it, I mean, it is brighter for us because it's so close to us. So that is the reason, right? Now, having that in mind, so let's look at how we define a brightness of a star, right? So that was the previous slide was about the luminosity. Now for stars, even for the planets, this is true. We used to use a word called apparent brightness. Right? Apparent brightness is the amount of the star's energy that reaches a given area, right? Each second here on Earth. Now, when you talk about the apparent brightness, this is where the sun comes into play. The apparent brightness of the sun is higher because it's closer to us, right? So that's because you know that uh, when it is closer, you get more light from that, right? So the apparent brightness is defined in that way. Now, all the stars that you see up in the sky, even that image that I showed you for the constellation, those bright stars that belongs to the constellation Ursa Major, they looks brighter for us purely because of the apparent brightness, right? So we do not have any idea about their distances, right? And so if you look at the night sky, you will have a wide range of apparent brightnesses among the stars, right? And most stars are in fact so dim that you need a telescope to detect them. Some of them are very bright in the night sky, and some of them are actually very, very faint that you need a telescope to detect them. Right? So there is a range of apparent brightnesses for the stars. And so this third point right here exactly explains the question that I asked from you. If we have two stars of the same luminosity, right? And one is twice as far away as the other, it will look 4 times dimmer than the closer one. So this is a very simple concept, but still you need to understand, right? So assume that you have two stars with the same luminosity, and I have defined what luminosity means in the previous slide. And however, one star is twice as far away as the other star. Then what happens is when you observe it from the Earth, even though they have the same luminosity, the star that is far away from us will look 4 times dimmer for us in terms of the apparent brightness, right? So now you should understand that when you calculate or define the apparent brightness, we are not taking the distance into the consideration, right? So we just look at the apparent brightness. And this is why actually the stars that are far away seems to be dim, and all of you know this. So this is due to the inverse square law of light, because when the distance is so far away, the same light will be distributed in a larger area, and this relation will be 1 over r squared, right? So 1 over distance squared. So basically you will get the same amount of light, but it will be distributed when you go far and far away. So that's what happens. Right. Right. Now we know, we have an idea about the luminosity and the apparent brightness, right? And the one that you can easily detect is the apparent brightness now without having an idea about the distance. Now, even in this case, astronomers had an issue, like, because in a science, when you do science, you just cannot tell that, okay, this one is brighter than that one, like that, right? So you should have a way of quantitatively measure something, right? Like the mass and other things that we use in day-to-day life. Now we are going into that phase now. Now this process of measuring the apparent brightness of the stars, we have a specific name for that. So that is called photometry, right? Photometry means this measuring the brightness, right? We can actually always tell that this one is brighter than that one and that one is brighter than the other one. But there should be a mechanism for that, no, to make these measurements. Now this photometry, the subject photometry began with Hipparchus around 150 BCE. So that's a long time ago. So what he did was actually he prepared a catalog of 1,000 stars. So he observed 1,000 stars and make a catalog. So what he had in this catalog is actually not only the positions of the stars, but also the estimates of the apparent brightnesses of the stars, right? So he include the position of the star on the sky plus the apparent brightness values, right? Uh, Now, when he record these brightness values, what he did was he sorted the stars into 6 brightness categories, right? So because there is no way of, comparing them other than having a mechanism. So what he did was he made all these stars into 6 brightness categories, and each category which he called a magnitude. So each category he called a magnitude. So this is how this magnitude scale came into play to measure the star's brightness, right? So what he did was actually, once he categorized all these stars into 6 categories, the brightest category he gave a number. So he called that those brightest stars as the first magnitude stars, right? And when it goes to the faintest category, these faintest category are the stars that you can barely see from your naked eyes, right? And he gave the number for those stars as the 6th magnitude stars. So his magnitude scale is between 1 and 6. Then the brightest stars he gave a number 1, and the faintest stars he gave a number as 6, right? Now, during this 19th century, astronomers attempted to make this scale more precise by establishing exactly how much the apparent brightness of the 6th magnitude star differs from that of the first magnitude star. Now, in Hipparchus' time, he just categorized these and gave numbers, right? And then later, astronomers tried to make this scale more precise. So, what they were looking at is uh, how much the apparent brightness of the 6th magnitude star differs from that of the first magnitude star, right? And so what they had was that uh, the first magnitude star has 100 times more light compared to the 6th magnitude star. So that was their finding, right? Now that's what I have highlighted here. The difference of the 5 magnitudes correspond to exactly to a brightness ratio of 100 to 1, because the 6th magnitude star, you have the 6th magnitude star, and then you have the first magnitude star. So the difference of the magnitude are actually basically 5 magnitudes, right? 6 minus 5 is equal to 5. 6 minus 1 equal to 5. And these 5 magnitudes correspond to exactly to the brightness ratio of 100 to 1, right? So that is their finding. So based on this information, they have this equation at the end. So that means if M1 and M2 are the magnitude of two stars, then we can calculate the ratio of their brightness using this equation, right? So this is based on the previous fact. So the difference of the brightness will be equal to 2.5 times log B2 over B1, right? So B2 over B1 means basically the ratio of the brightness, right? And then you can also derive that this expression for the brightness ratio in this way, like B2 over B1 equal to this equation. By the way, there are other forms of this equation, or any of the forms will be okay as long as you use it in a proper way, right? Now, this equation will be very important for you. Normally in astronomy, we don't provide these kind of equations in your exam papers, right? So these are like F equal ma type equations in astronomy that we expect all the students will remember after following a course, right? Because of that, make sure that you remember this equation, and I am sure that you will have to use it at some point, right? At least a different form of this in an exam. So make sure that you remember it, right? So M1 minus M2, you don't have to remember all the equations as you understand, right? So once you remember one, you can derive the others. Right? So basically M1 minus M2 equal 2.5 times log B2 over B1 should be enough, right? And I have given you a question here as an example. Uh, uh, if on the night sky, this is actually a real situation. If you go and look at the night sky, there are two bright stars, that is Polaris and Sirius, right? It is a common misconception that the Polaris is the brightest star in the sky. Polaris is the North Star, and we have a special, consideration for that star. And because of that reason, people used to think that Polaris may be the brightest star in the sky. So that's why we are so concerned about the Polaris. But this distinction actually belongs to the Sirius, and Sirius has a magnitude of minus 1.5. And the question is, how does the Sirius apparent brightness compare to that of the Polaris? So you need to find uh, the brightness ratio of these two stars. How bright is Sirius compared to the Polaris, right? Uh, can you try this yourself and tell me the answer? I will give you 1 or 2 minutes just to try it yourself and find the answer, right? So you are given the magnitude values. So try it yourself and see whether you can find the answer, right? So I'm going to give you like 1 or 2 minutes for this one. I have one answer from you, but I would like others to try that as well and see what kind of answer that you get, right? Right, two answers. How about the others? So please try this, right? Because this will be really helpful for you even in exams, since you know how to do it. You don't need to worry too much about, going back and practicing all these things again and again. Right, so I have two answers. Actually, if you do it correctly, you should have an answer. I think one of your answers are correct. The other one, please check. I think most probably this will be a arithmetic error. Uh, so the normally, if you do it, all you need to do is plug the value of 2 here and then plug the value of minus 1.5 here. So that is where you need to be careful, right? Right, thank you. I have another answer. Seems to be correct. So just for you, for any of you, don't get confused with this equation. You can see the B2 is right here and B1 is right here. So whatever the value correspond to B2, you can see here the B2 should, the magnitude correspond to B2 should go into the second one right here, M2, right? So basically what you need to do is just get magnitude 2 right here and then minus, and then M2 magnitude will be minus 1.5, right? So that is where you need to be careful. Here is a minus sign already here. So that means the two minus signs will become plus here. So you will have 3.5 multiplied by 0.2. So you will get 100 to the power of 0.7 or something like that. And at the end, once you calculate, you will see that the series is approximately 25 times brighter compared to Polaris, right? I mean, you will get around like 25.12 if you do it exactly, but the approximate value will be around 25 times brighter, right? Those who got it wrong, probably maybe for two reasons, maybe you ignore this minus sign right here. Remember in the previous slide, we talked about stars between the first magnitude and the sixth magnitude, right? And the difference of those magnitudes are 100. But this is the case what Hipparchus did at his time without having any new technology or something like that. But the one thing that you need to note here is when you define the magnitude scale, he gave the number 1 for the brightest one and number 6 for the faintest one. So this is the reason actually still we are using the same scale by developing it. And because of that, when you use magnitudes in astronomy, the lower numbers are always the brighter, right? So make sure that you understand it. So that is one important factor. Now, actually, we know that the region that he defined from 1 to 6 is only for the limit for the naked eye, right? But now we have magnitude values more than that we can observe from the telescopes right here. Right. So that is the magnitude, the equation that we talk about now here. So this is why you get this 25 times brighter, the magnitude minus. But another thing that you need to understand here is you can, both of these stars you can see up in the sky from the naked eye, so that you can get an idea. Even there is a star or a planet which has a magnitude of 2.0, you should be able to observe it from your naked eye, right? Minus 1.5 means this is even more brighter, because the lower the number you mean, that means the brighter the object, right? So you should be able to observe that as easily as well, right? Now having this magnitude scale for the apparent magnitude, so these are called apparent magnitudes, by the way. having this scale in mind, let's look at what kind of magnitudes that we have, some of the familiar objects, and I mean some of the telescope limits that we can observe, right? Now the first one that came into mind should be our sun, right? You can see the apparent magnitude of the sun is right here. I think the number is around 20 minus 26.5 in this region, apparent magnitude of the sun. And you can see that it is overwhelmingly bright compared to all the other objects, right? I mean, there is nothing even near in that region for the regular objects, right? And this huge minus value means that it is really bright. And then all of us know that the next brighter object that we have on the sky is the moon. So the moon is around minus 12 magnitude range. And then before all the other stars, the two of the two of the planets that you can see from the naked eye very easily. One is Venus. So that's brightness is very close to like -5. It should be -4 point something. And then the Jupiter and Mars are also easy to see up in the sky. So their brightness values will be around, -3 or 2, somewhere like that. And then you have the Sirius, the brightest star up in the sky. And then you have the Alpha Centauri. And then the Betelgeuse. Betelgeuse is one of the stars in the constellation Orion, right? The Orion constellation is hard to, observe in these days because it's not up in the sky at the night time. But this Betelgeuse is the brightest star in the constellation Orion, which you cannot observe in these days. But you can see that even Polaris comes after that, right? So we have this conception that the Sirius and the Polaris are kind of, the leading stars in the sky. But you can see that even the Betelgeuse is even more brighter than that, right? And the other thing that you will see when you get a chance, please look at this constellation Orion. And then Betelgeuse is the brightest star in one of the corners of the constellation. And at the same time, Betelgeuse seems to be a little bit reddish in color, right? And so that is something to note up in the when you see this constellation Orion. And then this limit right here, it is not an object. So that is the number 6 value that should be here. So that is the faintest object visible to unaided eye, right? Now this will give you having all these values in your mind will be very helpful in astronomy. So make sure that you get an idea of probabilities. Will be helpful to remember this diagram as well, right? And then you have something called a Bernard star. Bernard star is actually a star that has a larger proper motion, right? So you will understand what proper motion means in the coming lectures. And then from the binoculars, you can observe up to this limit. If you have a star that is close to a magnitude of 10, you can still see that from a binocular, right? Now, when you say a binocular, it has to be actually a binocular that you use in astronomy, not a regular binocular. But regular binoculars also you can see up to some point. But what this means here is binoculars that we normally use in astronomy, right? And so if anybody is interested, let me know. I can actually show one of these astronomical binoculars for you if needed, right? And then when you go into more faint objects, you cannot even observe those from binoculars. You need to have large telescopes. So when you go to the telescopes like to magnitudes like close to 20 and 25, you need 1 meter or 4 meter telescopes, right? I mean, that is the limit for those telescopes. Even from the 1 meter telescope, you cannot go beyond like 18, right? So if you go into more faint objects like up to 25th magnitude, then you need to have a 4 meter telescope, right? And when I say 1 meter and 4 meter telescopes, I am under the impression that you know what it means, right? Because we have discussed what those things means in previous lectures. And then we have a Hubble and Keck telescopes that's around like 30th magnitude. Hubble telescope is, by the way, a space telescope, and the Keck telescope is one of the larger telescopes that is actually located in one of the mountains in Hawaii Islands. And so I hope you can get, now you have a good idea about these brightnesses that you see up in the sky and the magnitude scale, right? And how to deal with these, right? Now this is really helpful when you see up in the news. Sometimes when you look at the astronomical news, they used to tell that, remember that I shared with you a news about the transit that is going to happen within these 2 days in the planet Saturn. And I told you there is a particular moon that's going to go in front of the Saturn, but we will not be able to see it from the naked eye. You need to have a telescope with a larger aperture, right? So the reason was actually that that particular object has a magnitude range close to 10 or 12. So which means around this region right here. So that means combining all the other effects from the atmosphere and the light pollution, you need a little bit larger telescope. No, you don't need a 1 meter telescope, but like a 12-inch or something like that telescope to look at that particular incident, right? So that is why practically it is important for you to get an idea about these magnitudes, because if there is a news that there is a new object appearing in the sky with a magnitude of, let's say, 8, so they just tell the number, right? So that's how they communicate it. But if somebody asks from you whether you can see it, let's say there is somebody who haven't followed astronomy as you, but they are thinking to observe this object from the naked eye just because they have heard it in the news. Now you should be able to tell that if it is in the magnitude range of, let's say, 12 or something like that, you should not be able to observe it up in the sky from the naked eyes, right? So otherwise these people are looking at the sky and will not see anything, right? So that is why you need to learn these things, and that is how you apply those things in your day-to-day life, right? Right. Now, so I basically explained you the magnitude scale that we normally use in astronomy. However, that is not the only scale that we are using to measure the brightness. Normally, this magnitude scale is mostly used for visual astronomy. So that means for the visual region or the visible region of the electromagnetic spectrum. However, astronomy is not limited to the visual region, as you know. We have radio telescopes, we have X-ray telescopes, we have gamma ray telescopes. So we are working, astronomers work all over this electromagnetic spectrum at different regions, right? And these different regions actually use different kind of units for different purposes. For example, when you consider about the radio astronomers, they measure the amount of energy being collected each second by each square meter of a radio telescope, and express the brightness of each source in terms of, for example, watts per square meter. So that's how they explain the brightness. And also for the IR and X-ray and gamma ray astronomy, they use energy per area per second rather than magnitudes, right? So these are actually for different purposes that they do it. But I do not have time to explain all these things. But I mean, just as an introduction, keep in mind that there are other ways of expressing the brightness in different regions of the electromagnetic spectrum in astronomy, right? Keep in mind that everything that I am telling here is, I mean, basically focused and related to astronomy and astrophysics, these measurements and everything, right? Right. So that's about measuring the brightness and the magnitude, how the brightness is related to the magnitude. Now I'm going to talk with you how to measure the distances for these stars. Now, before I move into that, anybody have any questions up to here? Any questions about measuring brightnesses and distances, those kind of stuff? Feel free to ask if you have any questions up to here before we move on to the next section. Remember that this section is very, very important, right? Because everything that we are going to talk after this section will be based on these measurements and these measuring these distances, brightnesses, those kind of things, right? So that's why in understanding and get a clear idea about these the distances and the properties are important for us to move on to the next section. Right, so if you do not have any questions, let me move on to the next section. Right, all of you should have this question in your mind that how we are going to make measurements to these stars, right? So there is no way that you can hold a tape and measure these things like we do in our day-to-day life, right? There are different ways of measuring distances in our day-to-day life. Even the for the kilometers, I mean, even for 100 kilometers, you can measure. There are mechanisms to measure that, but these objects are, we can barely see these. I mean, how we are going to measure the distances, right? Now, remember that measuring distances is a completely different subject in astronomy. So you have to use different techniques to measure the distances, and you need updated technology to measure the distances, and also measuring distances at different levels in astronomy is also different, right? Now, for example, uh, measuring distances to nearby stars, we use one method, but you cannot use the same method to measure distances to nearby galaxies, right? And you cannot use the same distance that you use to measure the distances to nearby galaxies to measure the galaxies that are so far away, right? So we have different advanced techniques to measure the different distances, and you will learn those one by one when you need those, right? Now here in this particular chapter, I am going to talk with you how to measure the distances to these nearby stars, right? Especially the stars within our Milky Way, right? And as you know, what I am trying to tell you is even these nearest stars are so far away from us, we cannot travel for those stars to make a direct measurement. So therefore, most of the times astronomers make indirect measurements or indirect methods to use indirect methods to measure these distances, right? And one of the most simplest and most precise techniques that we use to measure distances are called parallax, right? And I hope most of you may have heard about the parallax angles before. And basically, we are using the same technique here to measure the distances. And you will see a very important aspect in this particular method. Number one, you will understand how simple is this method, and I'm going to show you, even though this is simple, how these very advanced surveys and telescopes and even the satellites use this method to measure distances, right? Which is very interesting. And of course, the parallax is defined as the apparent displacement of a nearby object relative to more distant object as the observer's location changes. And what this means is you should probably understand from this picture, when the observer location changes for a particular, and when you are looking at a particular object from two different locations, then you will create an angle which you can use that angle to measure the distances, right? Uh, Let me first go into this particular diagram to make it clear. And you can see the sun is at the center right here, and then you have a nearby star at this particular location right here, and you are going to measure the distance to this particular star. And from this point right here from the earth, you create this angle with the sun. And then when it comes to this point right here, again, you create another angle that goes to the other side. So with respect to background stars, you can measure the angle, right? And I think this particular method, this seems to be very simple. And this is how you are going to measure it. If you have an object with the parallax angle of 1 arc second. So I hope you understand what degree means, and then arc means an arc seconds in angles, right? An object with the parallax angle of 1 arc second lies at a distance of 3.26 light years. Normally, when you have an object with the parallax angle of 1 arc second, that object is at a distance of 3.26 light years away from us, right? And this amount of light years, 3.26 light years, is called 1 parsec. So there are two different things that we are going to learn here. I am introducing a new unit for you. So that is the unit parsec. Right? Parsec is a regular unit that we use in astronomy. So 3.26 light years will be equal to 1 parsec. And the way that it connects to the distance is that if you have an object with a distance at a 0.1 parsecs, it has a distance. So it has a sorry. So let me correct myself. So if you have an object which has a parallax angle of 0.1 arc second, it will have a distance of actually 10 parsecs, right? So the way that you calculate it is you have to just use this equation, right? So I'm only giving you the equation here, but this equation is very simple. If you need to look at how you can prove it, it's a very simple proof. You just go and look at it in the internet. It's everywhere, right? But the idea that I want to convey here is using this small or simple mechanism called measuring the parallax angle, you can find the distance in this way, right? So if you can measure the parallax angle, you can find the distance. There is one important factor here that you need to make sure that you understand and remember. When you are using this equation in astronomy, you have to plug the value of the parallax angle in terms of arc seconds here. So make sure that you only use arc seconds. I mean, you can of course use the other units, then you have to do unit conversions and all kind of things. But if you plug the values in terms of arc second for the parallax angle here in this equation, it will automatically give you the distance in terms of parsecs, right? So D is for the distance, and this is why I have given the units inside the brackets. So this equation is basically D equal 1 over P. P is the parallax angle, but it is always important that you, each and every time that you use this equation, you have to use arc seconds. So if you are given a parallax angle in different units, let's say in terms of degrees, make sure that you convert it to arc seconds before you plug it to here, right? Then your answers will automatically come in terms of parsecs. And once you have the number in parsecs as for the distance, if you need to convert into light years, you can do it, because 1 parsec is equal to 3.26 light years, right? And I just have one slide like defining the angles, what arc second means, those kind of things. So I'm not going to go through it. This is in case if somebody needs it, but I don't think you need it. You already know about what arc second and arc minutes means, right? And this diagram that I showed you previously also explains what I mean. Basically, the idea came from the fact that from sun to earth, we have one astronomical unit from here to here. And here is the parallax angle that you are going to measure experimentally. And then you can calculate this distance, right? Because you know the parallax angle, this distance, right? right? Now the other thing, now you can clearly see that you can use the parallax angle to measure the distances. So something that you need to look at here is, what does the parallax angle depend on? So how does this parallax angle change with the distance? As the equation here shows you, you can see that the distance is inversely proportional to the parallax angle, right? So that means the larger the distance, the parallax angle will get smaller and smaller. It's obvious, no? If the distance is larger, right, in this case, this angle will be smaller, right? But if you are looking at a nearby star, the parallax angle will be larger, right? So this is something you experience in even in your everyday day-to-day life, right? So that means if we are going to measure the parallax angle uh, from an instrument, some kind of instrument, there should be a limit. There will be a limit for that, right? Because when you try to measure this parallax angles for stars that are so far away, your parallax angle will get smaller and smaller. And all of you know that even from your physics experiments in the lab, there are instruments that you use. There is always a minimum measurement that you can get. For example, like for the vernier caliper, those kind of thing, right? So that depends on the sensitivity of the equipment. Like that, here also you can measure the parallax angles, but there will be a limit for that you can go, right? So this is why you cannot use the parallax angle measurements to measure the distances for all the objects in the universe. Because if certain stars or other objects are so far away from us, this parallax angle will become very, very small. And because of that, it will be hard to measure, right? So that is the idea. So that's what I have mentioned here. The closer an object to you, the greater its parallax angle. So the parallax angle will be greater if the object is closer, right? So the parallax angle is inversely proportional to the distance, as I told you. So I guess, right. Now this is how you use the parallax in astronomy. In order to have the largest baseline possible, we can observe the stars from opposite side of the Earth's orbit around the sun, right? So that is what we can do. In order to have a very large baseline, you can use the opposite sides of the sun, uh, opposite sides of the Earth's orbit around the sun to measure the parallax angle, right? So that basically gives you a baseline of 2 astronomical units. That's because, you know, the distance from Earth to sun to one side will be 1 astronomical unit. So for the 2 sides, it will be 2 astronomical units. Right. Now you probably have question. I can, you know, I can introduce a lot of methods, but are these things actually used in astronomy or any other way to measure the distances, right? I mean, what do you think about that? Because I mean, it is easy to mention things in theory, right? But what we have to look at is whether astronomers actually use these methods in today's astronomy. Whether you are actually going to use it, otherwise, no point of, you know, learning something. No, you can just learn it, but if you cannot apply it, so let's look at whether astronomers are using these parallax techniques to measure the distances to nearby stars, right? Now, actually, we have measured the parallax angles, or we have measured the distances to thousands of stars I mean, before 2000, before the year 2000, we have used this, even before the year 2000, we have used this method to measure the distances to stars, right? Thousands of stars. One example is that uh, Proxima Centauri. Now, the Proxima Centauri has the largest parallax of all known stars for us. Why is that? Anybody? I think you should understand now that Proxima Centauri has the largest parallax angle to all known stars. That's because that should be the closest star for us, right? So these are things that are connected each other. And this parallax angle measured to be 0.77 arcsecond. So if the number is the arcsecond, 0.77 arcsecond, now you can directly measure the distance, right? So the distance should be 1 over 0.77 arcseconds. So that is the distance. Can somebody calculate that distance and tell me what will be the distance to the Proxima Centauri in terms of parsecs? How many parsecs will be the distance to the Proxima Centauri? So I will give you like 30 seconds, right? So try to calculate the distance to the parsec, distance to the Proxima Centauri in terms of parsecs, and then let me know the distance. So just, I mean, let's see, just for fun, right? It's a direct calculation now. Right. So anyway, let me just give you the, yes, I have one answer. Thank you. So it should be around 1.3 parsecs, right? Now, if you need to look at how many light years away this particular star, you just multiply this number by 4.26, right? Because there are 3.26 light years for one parsec. So that will be around 1.3 times 1.3 times 3.26 will be around little bit more than 4 light years away, right? So that is the closest star for us, right, in our neighborhood. I mean, except the sun. Now, would you believe me that there was a satellite called Hipparchus that we sent to the space specifically for this task, right? So that is actually to measure the distances to different set of stars using this parallax method. So there are instruments inside that Hipparchus satellite. I mean, this is done even like, I guess, 30 years ago. So Hipparchus was able to measure the parallax angles of 100,000 stars in our Milky Way. And this particular telescope has a precision of about 0.002 arcseconds. So that means these instruments inside these Hipparchus satellites were able to measure parallax angles as small as 0.002 arcseconds, right? So that's how astronomers have developed the technology. And that means 1 over 0.002 arcsecond means 500 parsecs, right? If you do the calculation. So that means any star up to 500 parsecs, we can measure the distances. Most of the stars up to that amount, we have measured distances from this Hipparchus satellite, right? Now, is that all that we have used? Actually, that is not the case. So this was the first satellite that we sent. Now, believe me that we have been able to measure the distances to stars in our Milky Way, and we have measured the distances for about 1.7 billion stars now using this method, right? So you may not believe me, but I will give you the evidences. At the same time, I have mentioned the techniques for measuring distances for more remote stars and galaxies will be discussed later in the course. So that means even though we have measured the distances to billions of stars using this method, you cannot use this method to measure the distances to remote stars and galaxies. So that means maybe the galaxies that are so far away from us, we cannot use this method because then this parallax angle will become very, very smaller. Our instruments are not sensitive to measure that much of smaller angles, right? However, there is one recent satellite that we sent to space, basically sent by the European Space Agency. And this satellite was able to make the measurement of 1.7 billion stars. So they have measured parallax angles of around 1.7 billion stars. And let me just show you a small video clip. For that, I actually have to, right? So I have restarted the recording, and what I was actually trying to show you is that one of the recent surveys, which we call Gaia survey, basically a satellite that was sent to the space to measure the parallax angles of these stars and to find the distances. And there are other things that this particular satellite measures, but the parallax angle is one of the primary things. And the idea is actually this particular instrument is unbelievable. Actually, it can measure the parallax angles that are so small that it can measure the distances up to 8 kiloparsecs from the solar system, right? And this distance is roughly 8 kiloparsecs, means a large amount of light years if you convert it, right? It's around close to 30,000 light years. And now if you get the the scale of the solar system, this is actually like measuring the distances to stars starting from the solar system up to the center, towards the center, close to the center of the galaxy. So it's a huge distance, right? So you can see that these the take-home message for you is that these are very simple mechanisms, but still you can develop these mechanisms to make these huge instruments at the end that use the same simple principle, right? So that's what I want to share with you, right? So that's the story about measuring distances to nearby stars using parallax angles, and I have shared with you. Let me share this presentation again, right? So I guess all of you can see now my screen. So we have been talking about the parallax angles. Now we know two things, right, from today's lecture. So that is how to measure the distances to nearby stars, and how to make a measurement about the apparent brightness of a star, and how to convert it to a magnitude, and based on the magnitude values, how can we decide whether that particular star may be visible or not for us from the naked eye, what kind of instrument that we need to, look at that particular object, those kind of things, right? So those are like, the practical things that you need to relate into this particular lesson and try to understand, right, how these things are applied in your, applied in different places, right? Now we should have a question. Now what we have learned up to now is measuring the apparent brightness of a star, an apparent magnitude. This is okay, but there is still a problem, right? Because when we need to compare the brightness values of two stars, as you can see, apparent brightness is not the best way to compare the brightness of two stars, right? For example, we have our own sun in our solar system. It seems to be very bright compared to the Sirius, but when you look at the actual luminosity values, it is, we know that the sun is not the brightest one. The luminous is more bright, the Sirius is more bright, right? And because of that, we should have a way of comparing these actual brightness values, right? Now, this is where the absolute magnitude comes into play, right? If you assume that the distance can be measured to a given star, then we can use this information to compare the intrinsic brightness of different stars. Now, previously, the problem was that we did not have any idea about the distances to these stars. So we have to just use the apparent brightness. Now, with the development of this method, using this parallax method, now we know that we can measure the distances to stars, right? Now, once we have the idea about the apparent brightness of a particular star and the distance to that particular star, it is obvious that we can get an idea about how to measure the intrinsic or compare the intrinsic brightness. So this is the same thing as the luminosity of different stars, right? So our goal should be here is to remove these effects coming from the distances then, right? Because these different brightnesses that we have is primarily because of the different distances, right? And once you remove the effect from the distance by treating all stars as they have at the same distance, then the brightness value converted to the magnitude scale in that way is called the absolute magnitude. So previously what we have measured is the apparent magnitude, right? Now we can measure the absolute magnitude in this way, right? And there is a definition for that. Absolute magnitude is defined as the apparent magnitude that an object would have if it were at a distance of 10 parsecs. So if there is an object at a distance of 10 parsec, then once you keep that particular object at the 10 parsecs distance and measure the magnitude, that particular magnitude is called as the absolute magnitude, right? Now the important thing here is in this way, when you compare the brightness or the magnitude values of the stars, we are going to keep all the stars at the same distance to make a fair selection, right? So then when everyone is at the same distance, in here, according to the definition, that distance is 10 parsecs, and then you measure the brightness or the absolute magnitude, then the comparisons will be very fair, right? So that is the idea here. Now you can actually uh, define this distance magnitude relationship to find the absolute magnitude in that way. So in order to determine the absolute magnitude of a star, we need to know its apparent magnitude and the distance, right? To define an absolute magnitude, we need two things. Number one is the apparent magnitude, and number two is the distance. Now we know that from our previous discussion, we can find the apparent magnitude. There is no issue with that. And from the parallax method, we can find the distance, right? So once you know these two quantities, you can easily find the absolute magnitude one, right? Now to relate these quantities, we need only account for the inverse square law dependence of the brightness on distance. Everybody knows that, right? Apparent brightness is proportional to 1 over d squared. And we also know that the apparent magnitude scale is a logarithmic scale. A factor of 100 in brightness corresponds to a difference of 5 magnitudes. So that's what we have learned before, right? So that means by combining all this information, you can write the mathematical relationship between the apparent brightness and the absolute brightness, apparent brightness and the apparent magnitude and the absolute magnitude in this way, right? Capital M equal simple M minus 5 log d over 10 parsecs, right? So the M is the apparent brightness and capital M is the apparent magnitude. M is the apparent magnitude and capital M is the absolute magnitude, and d is the distance of that particular star, and 10 parsecs is that came from the standard definition that we have, right? So make sure that, and this is again one of the very fundamental equations in astronomy to measure the distances. So therefore, you need to remember this equation, right? Of course, you can derive it from previous equations, but it is always easy to remember this kind of equation. So this is another equation that is kind of a standard equation in astronomy that you need to know what each of these terms mean and remember it, because this will be regularly used to find absolute magnitudes and sometimes distances, those kind of things, right? Right. Now using this equation, you can actually please try this particular example yourself as well, right? Due to the time limitations, I am giving you how to do it, but make sure that you try it yourself as well. This is one of the good examples to the question that we talked before about our own sun. Remember that in that scale bar, our sun had an apparent magnitude of around minus 25. So its actual apparent magnitude is minus 26.7. And what we know is that the sun is at a distance of 1 astronomical unit from Earth, right? Now, I have given that there are about 206 times 265 astronomical units in 1 parsec. Now, these kind of unit conversions I will give if needed, right? So you don't need to remember that. But for here, make sure that you know 1 parsec equal to this much of astronomical unit. Now, having all this information with you, I have a question. What is the absolute magnitude of sun, right? So you know the apparent magnitude and you know the distance. Now you should be able to use this equation right here. You have the apparent magnitude, you know the distance. So you should be able to use this equation to find the absolute magnitude. Now, most important thing here is when you plug the values for the distance here, the unit of the distance should be in terms of parsecs. These are the things that most of the students get wrong in astronomy. All of you, I mean, it's obvious for you, even in terms of mathematics, you should have the same units in here and here, right? But make sure that this unit should be in terms of parsecs here. That is something very important, right? And if you plug all the values, this will give you a value of absolute magnitude equal to 4.8, right? Now, you may be surprised that when this is the absolute, if you can consider the absolute magnitude of the sun, so that means if you keep the sun at a distance of 10 parsecs, because sun is very close to us now, it's even not 1 parsec, it's less than 1 parsec. It's a very small value in terms of parsecs, right? But if you keep the same sun at a distance of 10 parsec, then we would barely be able to see it with the unaided eye even. If you remember that this diagram right here, if it is 4.8, so that means it should be close to 5 right here, right? So that means it is kind of in the limit of the object visible to the unaided eye, right? If it is like 5 or 6, then if you need to observe it, you have to have really dark skies from the unaided eye, right? So that's why now you should understand that fact about why sun is brighter compared to why sun is brighter for us. That's because that is closer for us, as you mentioned. However, if you take the absolute magnitudes for the comparison, sun will be a very tiny object in the sky, which is barely visible for us, right? And so I have given another example in the bottom. If you have a star that is at a distance of 10 parsecs, then your apparent and absolute magnitudes will be equal to each other, right? I mean, that's the definition now. It should be obvious, right? Up to now, anybody have any questions now? So I'm going to stop the lecture from here because we are going to talk about a different section on the next day. That is about the color of stars and spectrum. Anybody have any questions? Remember that this lecture material is already available in your Google Classroom, right? Anybody can download and go through it even now. And keep in mind that this section that we have discussed today and also the next section that we are going to talk are very important for you for your coming lectures, right? Because these are like kind of measurements and properties that we are going to use very regularly to discuss different properties about stars, right?
So now we have learned about the how to measure the brightness and the distance to a star today. And on the next day, we will talk about how to understand the color of a star, and also like temperature, and also some spectral features like spectrum of a star and then the size, those kind of properties, right? To finish this section. So those are the things that we are going to talk on the next day. So if you do not have any questions, let me stop the class from here. So I may be, so I will let you know the date for the next lecture